Okay, so let me thank the organizers for inviting me to this nice place. So I'm very happy to be in IISc Bangalore. This is going to be the topic of discussion today. These are the list of things that I'm going to talk because of short time. And I want to sort of motivate why I have done this computation. If you all know that, for LHC physics, this is something you might have heard actually, that Drelian process is one of the important process for measuring, let's say, luminosity and things like that. And if you want to really measure luminosity, okay, you have to use a formula of this kind, and the formula contains, something called flux of the incoming partons in the incoming hadron states. Okay, the flux is defined by this. It's a combination of two PDFs, parton distribution functions, which basically parameterize the probability densities of the partons, quarks and gluons in the proton at given energy and given momentum fraction actually. That's how its flux is defined actually. And these two Fs, that appear here cannot be computed very easily actually in quantum field theory because it involves hadrons. We don't know how hadrons are made up of quarks and gluons, and we have difficulty to compute. It's just lack of our technical ability. Otherwise, in principle, it is a well-defined quantity and so on and so forth. Often these are extracted from the experiment because we don't know how to compute them actually. So this is an important part actually. Similarly, if you want to study TT bar production and then do a lot of physics, again we need this parton distribution function. This is another place we encounter PDFs actually. Of course, Higgs physics, if you want to discover Higgs, of course you can discover Higgs. If you want to really say that's a Higgs of a standard model or beyond standard model, we need to calculate this kind of cross sections, and cross sections involve PDFs. PDFs you need. Okay, so where do you get these PDFs from actually? There's also another function called fragmentation function. This tells you about how in a scattering you get hadrons in the final state actually. In any scattering, either you get leptons or hadrons, right? You don't get quarks and gluons. Some of quarks and gluons that produce in a scattering, okay, fragment into hadrons, and we still have not understood fully how hadrons are produced in any scattering experiments actually. This fragmentation process, how the things are hadronized is still an open question, and of course these are all actually sort of dumped into another function called fragmentation functions I call FF. Okay, so how do you extract these PDFs actually? If you cannot compute them, you should extract them from the experiments. One of the experiments is deep inelastic experiment. This is something that many of you may not have studied, because these days you study advanced topics in quantum field theory. This is what we studied when we were students actually, deep inelastic scattering, because this is only one of the most important scattering experiment that we could perform to understand the structure of proton, and we could extract the PDFs actually. Okay, so this is one of the experiments which dedicated itself for several years, maybe more than a decade, to extract these functions from an experiment called deep inelastic scattering experiments. And then we have this set of PDFs that extracted from the experiment. That is what we use actually for studying any LHC physics. Okay, or even for Tevatron physics, without these PDFs, we cannot make any statements. You cannot run any code actually. Okay, this is most fundamental. Okay, so this is an important part actually. Similarly, fragmentation functions. If you want to study any hadronization process, if you want to understand the final states, you need to know about this fragmentation function. That's also extracted from experiments. For example, E plus E minus experiments, like at CERN, there are LEP experiments, that actually could measure these quantities. That's also an important. Okay, so I'm going to tell you about some experiment where both PDFs as well as fragmentation functions can be extracted actually. That's this experiment called semi-inclusive DIS. This is not the standard LHC physics that we have been talking about for last 2 decades or so. This is another experiment which is actually, it's also done in CERN, okay, as a part of SPS. Okay, this is an experiment called semi-inclusive DIS. This is a scattering of leptons on a proton, on a single proton, and you can look at final states which have specific hadron like pion or a lambda baryon or whatever. Okay, so this process has an advantage of actually probing or are sensitive to both structure functions and PDFs, structure functions as well as fragmentation functions. So I'm going to talk about this process and what improvement that you can make in order to make a theoretical predictions as precise as possible, because this process can provide information about the the pattern distribution functions of this proton, and also fragmentation functions, how this final state quarks and gluons fragment into hadrons actually. So this is a kind of a bonus where you have both together actually. Okay, so one of the experiments that could probe this PDFs as well as fragmentation function. This is a compass at CERN, where they could use this SPS and perform this experiment, and there are data on this. Actually, there are minimal data which provide information about these fragmentation functions. And there is also fits from the experiments. You can fit it and get some PDF, fragmentation states that you can use it for your studies. Okay, so this is all good. So that justifies why I'm interested in SIDIS. Okay, why second order QCD correction? That should be a justification actually. I'll give you simple justifications. Okay, if you look at Higgs production, which is the milestone. Okay, of LHC. Okay, this LO cross section was known almost several decades back, 77, almost 4 decades back, and you can see it's so far away from the real value of the cross section, which means the theoretical predictions, okay, for such an important process, okay, was very, very different if you compute at leading order. So this tells you that we need to go beyond leading order and compute higher order corrections and make it to get the value which is very close to the experiment. So these are the measurements from the experiments of producing Higgs in PP collisions, and this is the leading order prediction, which is about 20 picobarn, and the real value is 50, and you can see how theory has actually prediction has matched to experimental. Without these computations you cannot do this. So cross sections computations with hadrons in the initial states or in the final state are I would say it's unreliable if you restrict yourselves to leading order. So this is a kind of a warning actually, Higgs prediction. There are many examples that I can provide where leading order cross sections are completely unreliable if you want to actually compare it with experimental data, in particular for processes involving hadrons in the initial state and or in final state. Okay, so that's the reason why I actually got interested in looking at the semi-inclusive process and study the corrections to that actually, because if you calculate a leading order prediction from this, I can bet that it will be unreliable actually. You cannot use it for any sensible purpose actually. Okay, so this experiment, of course, it's not academic. It's going to be very interesting soon because EIC is coming up actually. This is electron ion collider at Brookhaven, and it's going to bring a lot of physics, and this is one of the processes that is going to be studied in detail, and we will get very, very interesting physics out of it actually. Okay, so that's one of the reasons why actually I looked at semi-inclusive DIS and second order corrections to this actually. Okay, so what is second order corrections actually, or first order corrections for that matter actually. So semi-inclusive process, as I said, is going to bring you a lot of interesting things about the structure of hadrons, and also how quarks and gluons fragment into hadrons. Okay, and the only way you can compute these cross sections is using QCD, because these initial states are protons or whatever ions that we start with, and we have fully understood the physics of QED or standard model, because those are actually not composite stuff, so you can easily compute things in perturbation theory, unlike QCD. QCD comes with these non-perturbative quantities. Okay, so hence we need to work hard to actually make statements about this. That's where what Anand's talked about comes in. You need to know a lot of mathematics to actually perform computations, because you need to go beyond leading order, which involves a lot of Feynman diagrams and integrals and so on and so forth actually. Okay, so what these calculations do, when I say it's important, it is important because it reduces uncertainties. Where these uncertainties come from? The uncertainties comes from renormalization scale that you all might have encountered in when you run these codes. You fix some renormalization scale, mu of is equal to some value, mu r is equal to some value, and choose PDFs. All these things are actually unphysical quantities. All these unphysical quantities give you physical quantity because we know these cross sections to sufficient order in perturbation theory. If you truncate, of course they will be sensitive to all these unphysical quantities. Okay, so all these uncertainties, if we want to sort of have control, we need to add more and more terms in the perturbation theory so that it's reliable. Okay, so that's one of the reasons. So if you look at the work of Alterelli, which is about 4 decades before, their intention was to actually give a prediction for semi-inclusive DOS. They gave predictions for many important processes even before all these experiments were set up, actually PP collisions or PP bar collisions and things like that. Okay, these were the earlier papers on this topic. The NLO was computed along with many other processes by Alterelli, Ellis, Martinelli and Pi in 1917. It's almost 4 decades before. And later on, actually, because there are new experiments coming up with the E plus electron proton colliders, deep inelastic scatterings, then there are some papers which try to actually go beyond leading order, actually, next to leading order. These are the two works. Okay, so recently we actually got into this exercise of performing next leading order corrections. The reason is again that even next to leading order are unreliable. So we have a couple of papers. One of them, as you see, that it has got some attention because this process is now very interesting in the physics community. Of course, in the US, this is a flagship program, so there are a lot of interest in actually getting into this project and then contribute actually. So I welcome you also to join, because there are a lot of opportunities. Okay, so let's look at this semi-inclusive DIS. Okay, this is basically proton going to electron plus some hadron. It could be pion or lambda or whatever, and it factorizes into leptonic part and the hadronic part. As the picture shows, there's a leptonic part which can be separated from the hadronic part just by the photon exchange. Okay, the pattern model tells you how to express this hadronic cross section in terms of calculable partonic cross sections, and all you need to is these two functions f and d. That's what I described in the beginning. F is PDF, it tells you about how partons are distributed inside the proton, and D is the fragmentation function. It tells you about how a parton of type B fragments into a particular type of hadron. And these two are not calculable, and this experiment is going to help you to actually extract from this. Okay, and what is calculable is this, and what is measurable is this. Okay, having obtained this perturbatively calculable curly f's, you can plug in here, keep this d's and f's as unknown quantities, compare it against the experiment, and extract d's and f's. Okay, that is how it is done actually in the experiments. Okay, and all you need to do is actually you need to compute this curly f in perturbation theory. That's what is going to be done now. Okay, so if you want to compute this f, you need to know this parton level cross sections. This is the leading order process for this particular process. Okay, and this can be written as phase space integral over the matrix element of certain Feynman diagrams, with a constraint that this final state hadron fragments into final parton fragments into hadron actually. So these are the typical processes, and this is unimportant as far as this is concerned. So you have several sub-processes contributions. 10 minutes. Okay, I'll finish it. So there are several partonic level processes, and which means that it brings you a lot of Feynman diagrams and Feynman integrals, and we need to do all of them actually to get the perturbatively calculable part. You can classify these Feynman diagrams into 3 classes. One is called the pure virtual, which contains all 2 loop diagrams that contribute to the process, and we have a pure real process where you have only real emission processes. And you can have some, combination of this mixture of real and virtual processes. We need to, calculate all of them actually by using some softwares actually, because, drawing them by hand and putting all the Feynman rules and all, that's very messy process. Now we have lots and lots of developments in this computer side. Actually, you can actually use packages actually to, compute them. Okay, so then what do you get actually? If you calculate Feynman diagrams, you get Feynman integrals actually. Feynman integrals can come in two forms, as a kind of loop integrals or phase space integrals. I would call both of them are Feynman integrals because loop integrals can be related in terms of, phase space integrals can be written in terms of loop integrals actually. So you have a large number of integrals. I think Anand spent a lot of time to explain actually how this can be done using very sophisticated packages and so on and so forth. Okay, all these things are very helpful, and without that packages, it is impossible to actually achieve this task. Okay, so there was also a question about how these integrals are evaluated. You mentioned about you can use integration by parts. Integration by parts is basically the simple Gauss identity. So you can actually write down every Feynman integral, okay, by demanding that it satisfy this equation because this is obvious in dimension regularization, and this gives you a set of relations among the integrals that you encounter in your Feynman computations. By using these relations, we can actually reduce the large number of integrals into smaller set of integrals, which you call master integrals that he mentioned in his talk. Okay, these master integrals are the standard way of getting a larger number of integrals to a smaller set of integrals actually. That was about the loop integrals. You can apply the same trick, this reducing large number of integrals to a smaller set of integrals by for the phase space integrals as well, because as I said, even phase space integrals are like Feynman integrals. If you identify all this delta function as some imaginary part of propagators of this kind actually. So by replacing all the on-shell propagators, on-shell whatever delta functions by the imaginary part of the propagators, you can actually reduce them to loop integrals. Again, use this technique of reducing them by master integrals to obtain the result actually. So that's one part actually. That is, all you could do is actually, if you have huge number of integrals, reduce them to fewer integrals actually. But you have to calculate integrals. Okay. So that's the next task actually. How do you calculate this integral? The standard textbook method is actually use Feynman parameterization or Schwinger parameterization, and sit and work hard actually to get the results actually. But now that standard tricks do not work beyond one loop, because there are only few Feynman integrals can be solved using those standard textbook methods actually. If you really want to solve any two loop integral or beyond, we need to actually resort to some modern methods actually. One of the modern methods which is extremely successful is this differential equation method. Basically, you actually convert all your master integrals, Feynman integrals, as functions that satisfy certain differential equations, which Anand actually mentioned in his talk actually. So you can actually write down integrals as solutions to certain differential equations, okay, provided you recognize the external momenta with some scaling variables actually. So if you can identify certain scaling variables, you can set of differential equations out of Feynman integrals actually. This is called integration, differential equation method to solve Feynman integrals actually. You can show all your Feynman integrals can be expressed as first order coupled differential equations. That's the first step. So having done this, you can solve first order differential equations like a mathematician, okay, or an engineer, and then get your results for integrals. So you don't need Feynman parameterization, you don't need Schwinger parameterization and all that actually. All you need to know is actually boundary integrals for this set of integrals. Boundary integrals are integrals in some specific values of x. Okay, you can choose any value of x that you like, which can help you to solve these integrals. Okay, I can choose x is equal to infinity, or x is equal to 0, or x is equal to 500, whichever I would like. And of course the answer is independent of the boundary, as you know, the first order differential equations. So you can choose your convenient choice of boundaries and then keep manipulating and then get an answer to these integrals. So this is a clever way of calculating integrals using differential equation method actually. And these are the ones that really actually revolutionized this Feynman diagram calculations, and we got several important precise calculations, precise results for physics at LH in particular, through these methods actually. Without this integration by parts and differential equation method, we would not have actually claimed that X is the X of the standard model actually. This I can confidently say. Okay, so this is actually in a differential equation that some of the integrals that satisfy. Just to illustrate how it can solve, you can write down a differential equation like this. I is an integral, Feynman integral. Okay, S is an external variable, let's say center of mass, energy or whatever. And then you can actually solve this. This is a simple first order differential equation. Any first year graduate can solve, even a 12th standard boy can solve. And it's a series, you can actually make a series expansion around this, n is equal to 4, n is a dimensional regularization parameter. So expand it, and order by order you can actually solve. All you need to know is actually boundary condition. Okay, that's a tricky part, but that can be also be done actually. So calculating an integral at some boundary is easier than calculating the full integral actually. Okay, that's the whole idea. And now there are many modern and revolutionary ideas in this business. Okay, there's a work by Hen who basically showed by making certain gauge transformations on these matrices or these integrals, you can reduce this integral, this differential equations in some form called epsilon form, wherein you can actually pull out all the end dependency outside actually. So instead of working with a set of master integrals, you transform them to a newer set by certain gauge transformations, and then you get a new set of differential equations, and this new set of differential equations contain this end dependence, this dimensional regularization parameter just outside this differential equation. Then the solutions take a simple solution which is simply a path ordered. Okay, and so these Feynman integrals are very special. They are not standard integrals that you see in textbooks. Okay, they were so special that actually they are independent of this integral is independent of path. Okay, and you can actually choose a convenient path. Again, like you choose boundaries as for your convenience. You can also choose the path of the integration as you wish, because it's independent of path, and you can systematically compute. And there are some fancy ways of doing this, and it turns out that if you expand it, you get uniform transcendality and things like that. Okay, I will not go into the mathematics. If you just perform this integral, and you can also identify this A contains certain single pole terms by again making several transformation. It's called what they call Poincare rank. You can reduce the rank of this the pole of this function to 1, and then you can integrate this. That integral, the solution to this integral differential equation will give you a series which contains log square. Yeah, I'm through actually. Log square and so on. So you can do all this very beautiful mathematics, and finally you get an answer. So all I'm saying is actually what Anand was mentioning. To really get a number, you need to actually use a lot of mathematics, and you'll have to do a lot of analytical continuation and so on and so forth. Okay, there's a lot of complex analysis involved. Let me not go into the details. I'll show you the final result that we could do all that actually. Okay, because there are a lot of developments in the mathematics of calculating Feynman integrals, and thanks to that we have this plot actually at next to next leading order level, and it shows, as I mentioned, leading order is these dotted lines, and the next leading order is the one that you get from these results actually that we did. Okay, and you can see also this uncertainty is coming from various scales which look like a big band gets reduced actually. Okay, similarly these are the results for another similar process, semi-inclusive DIS, where you can improve your results by adding more and more terms in the perturbation theory. Thank you.